All right, welcome back everybody. We're having fun with arc length. Now we're going to talk about another important thing in differential geometry. And this one, admittedly, is also quite strange. It's a little complicated. There's a ton of formulas for it, which I'm not expecting anybody to memorize all of them, but it is an interesting concept called curvature. Curvature. So what is curvature? Well, it's a measure of how sharply a curve bends. So looking at this kind of weird looking line that I made right here, I would say that it's very curvy right at this point right here. It's very curvy right there. And it's maybe not quite as curvy right here. Looks pretty flat there to me. So it's a measure of how sharply your curve is bending. All right. Seems pretty straightforward. Well, let's make it more complicated, of course. So it turns out that the curvature is also the magnitude of the rate of change of the unit tangent vector with respect to the arc length, which is given by s, as you'll recall from my last video. So this is terrible. We use the Greek letter kappa to denote curvature. And again, this colon equals here means this is how we're defining it, is defined as the derivative of your unit tangent vector, which you'll remember had kind of a nasty formula, but with respect to the arc length parameter, which was also kind of difficult to find. That's the definition. Sorry that it can't be more beautiful than that, but there are some nice formulas that we'll see in just a moment. So first of all, this is equal to, I mean, here's just the magnitude of t prime evaluated at the arc length parameter. So t prime of s. Okay. The important thing here is, again, we have to be working with a smooth curve, and we talked about this in the last video too. So this just means things like we should have no sharp corners, no cusps, no discontinuities, nothing weird going on. Everything should be nice and beautiful. It should be differentiable. In fact, ideally it would be infinitely differentiable, but that's for another day. Okay, so it might not be surprising to you that a circle has the same curvature at any point. I mean, if you were on a circle, you would, and then on another point in the circle, it's just as curvy there as it was in the first place. And it turns out that the curvature and the radius of this circle, of any circle, they are inversely related. So, in other words, if you have a very large radius, if you have a really big circle, large radius, you can see that it would be flatter around the sides, so it's going to have less curvature. And the opposite would also be true. If you have a very small circle, very small radius, then you have quite a bit of curvature. Very curvy. So the first thing I want to do is let's show that the curvature of a circle with radius r is given by kappa equals 1 over r. So this is, again, showing that kind of inverse relationship. If you want to pause it here and try this, go right ahead. So you'll remember that for a circle, the parameterization is r of theta is equal to r cosine of theta times r sine of, or not times, excuse me, it's a vector, r cosine of theta comma r sine of theta. And hopefully you remember from your Algebra 2 days that the arc length on a circle can be found by simply multiplying r by theta, as long as theta is in radians. So you take the radius of your circle, multiply it by the angle that you're looking at, which angle, what part of the circle you're looking at, and you're in business. So rearranging this, we see that theta is going to be equal to s over r, s again being the arc length component, or the arc length parameter, and r being the radius. So substituting this back in, we get a very nice, well, maybe not so nice, formula for r of s. So r of s is going to be r times the cosine of s over r for the first component, and r times the sine of s over r for the second component. Again, you should check that this is in fact the arc length, and the way that we verify that, you remember, is that there's only one parameter, and that is the arc length, such that the magnitude of the derivative is equal to 1. So I'll let you all play with that for a little bit here. Take the magnitude of that derivative of this function and of this vector valued function, and you should get 1 out. And if you do, then we know for sure that we've got the arc length parameter. Otherwise, we did something wrong. But here we did do something right. This is great. So let's find this unit tangent vector. And you'll remember the formula for that is that it's r prime of s divided by the magnitude of r prime of s. But again, the nice thing here, since this is the arc length parameter, the magnitude is just 1. So the denominator is just 1. The numerator is just use a little chain rule, and we get negative sine of s over r comma cosine of s over r. This implies that the derivative of t, the unit tangent vector, just keeps getting worse and worse, doesn't it? A lot of derivatives going on here. But the derivative of that, again using the chain rule, is going to give us negative 1 over r times the cosine of s over r, and then negative 1 over r times the sine of s over r. And what we would like to calculate is the curvature, which is given by the magnitude of that vector. And you'll notice that, again, using this fact over and over again, that sine squared plus cosine squared is equal to 1, we get that the kappa is equal to the square root of 1 over r squared, which is just 1 over r. Yes, that's what we wanted to show. The curvature of a circle is 1 divided by its radius, and that's at any point along the circle. It doesn't matter where you are. It's got the same curvature everywhere. Okay, beautiful. So what happens if we don't have an arc length parameter? Well, I guess you could find it, but as you saw from the last video and from some of the work that you all been doing, it can be a little complicated. It can be a little bit hard to find the arc length parameter. So if you don't have it, you can use the following formula. Kappa is also given by the magnitude of t prime of t divided by the magnitude of r prime of t, which doesn't seem too scary, I guess, except that there's a lot of calculating to do there. For some insane reason, this is the same thing as the formula on your right. It's r prime of t cross the second derivative of r double prime of t, all over the cube of the magnitude of r prime of t. So just, I mean, so many calculations that you would have to do here. Take a derivative, take a second derivative, take a cross product of those two things, which could depend on t and be all sorts of awful. And then you're taking magnitudes of all those. It becomes a huge mess. But you can use this formula if you, again, do not have the arc length parameter. It's obviously more complicated, but it's also pretty complicated to find the arc length parameter. So I guess there's kind of a trade-off there. So what this means is that the curvature here, again, kappa standing for the curvature, it's the ratio of the rate of change of the tangent vector to the rate of change of the arc length. Ugh. And this, I mean, whoever came up with this is much more clever than I am, just trying to find a firm footing for how to define how curvy a shape is it's not an easy game. So clearly, I hope it's clear that the larger the length of delta t is, the change in your unit tangent vector, the more the curve is bending, and that's because your kappa is getting larger, right? So the bigger the kappa is, the larger the curvature is. How big can the curvature get, I wonder? I guess it could be as small as 0, which would be when you have just a straight line. But I guess, could curvature get infinitely large? I'm not sure. Something to think about. Maybe I'll put it in the problem set. We'll see. There's another formula, of course. So if you have just y as a function of x, so if you're back in single variable calculus, right? So you're just working with a function of one variable. Kappa can be found by simply finding the absolute value of y double prime. So because we're working with only one variable here, we don't have to talk about magnitudes. We can talk about absolute values. It's the absolute value of y double prime divided by 1 plus y prime squared, which should look familiar. That should look like sort of like the arc length parameter, but it's that raised to the 3/2 power for some insane reason. Why is this true? What is going on here? Well, let me see if I can illustrate what's happening. So imagine that we have a vector value function in 3 space, and it's given by x, y, 0. But we're assuming that y here is a function of x. So it's actually x, f of x, 0. So there is no z component, because then our function would depend on too many variables. So what does this mean? This means that r prime, this is something for you to check, is just going to be 1 comma f prime comma 0, which I think is pretty clear. And r double prime is going to be the vector 0, f double prime 0, which seems pretty straightforward. So if we go back to this kind of ugly formula where it was r prime cross r double prime over r prime cubed, so magnitudes of all those, I'm leaving off the magnitudes, but don't leave off the magnitudes when you actually calculate these. So I'll leave this kind of as a quick exercise. Take the cross product of r prime and r double prime, and it's looking like you're getting f double prime. We want to take an absolute value of that because we always want curvature to be positive. Excuse me. And so we take the absolute value of f double prime. And then let's see in the denominator what do we have going on here. The magnitude of r prime of t, again, that's something to just check here. Square all the components of r prime, add them together, take a square root, and that's what we have in the parentheses there. The formula tells us to cube that for whatever reason, and so we cube that. And then you see if we just replace f with y, then we get exactly the formula we wanted. We get y double prime, the absolute value of that, over 1 plus y prime squared, that whole thing to the 3/2 power. And that's coming from, I mean, just moving that square root outside, right? Calling it a 1/2 power. Nice little algebra 2 trick. Okay, so this is another formula that you could use for curvature in the rare situation that you have y as a function of x. Okay, so here's some definitions for you. So imagine that you have a curve with curvature kappa at the point P. Lots of letters floating around here. What this means is that there's going to be a circle with radius given by r equals 1 over k, 1 over the curvature, that passes through the point P on the curve's concave side. So can you all envision what's happening here? If we have some kind of a curve, let's say something like this. Here's a point. I'll put this right here at the bottom. This is the point P. The curve is the curve C. And what we've got here is we could draw in a circle. Let me see. I would say that this circle gives us a really nice idea of what the curvature is at that point P. And so what's happening is the radius of the circle, so from the center to P, the radius is given by 1 over kappa. And it's on the curve's concave side. It would never go on the other side here. We would never put the circle over here. That would be bad. It always goes on the concave side. So the radius of the circle we call, shockingly, the radius of curvature, and the center of the circle is called the center of curvature. And obviously, as you change what point you're at, if you're moving along this curve, both the radius and the center are going to be switching around. What this gives us is something called osculating circles, and this comes from the Latin word osculum, which I never took Latin before, but apparently means a kiss. Oh, how sweet. The circle is just kissing the curve. All these different circles are just kissing the curve. Something to check out this week is through Wolfram Alpha. There's a really nice demo of what's happening in both 2 dimensions and 3 dimensions. If you just look at your weekly tasks, you'll see a link to these things. You might have to download some software first, but once you get there, you'll see these curves that are just kind of, you've got these circles that just kind of move along them, that they change their radius, they change their size. It's very exciting. I'm also trying to make something like it on Desmos so that I can type in whatever function I want. So if you all are familiar with Desmos, I suggest you try to do the same thing as well. Let's see if we can make something awesome on Desmos. Okay, so let's do an example. Let's find the curvature of the parabola given by y equals x minus 1/4 x squared at x equals 2. So yeah, if you all want to try this yourselves before looking at the answer, go right ahead. You'll notice here that we have y as just a function of x, so I can use my new formula for curvature. It's given by y double prime over 1 plus y prime squared, all raised to the 3 halves. And so hopefully this is very basic, but y double prime here, the second derivative is just negative 1/2. So when you take the absolute value of it, you get 1/2, which is what's in the numerator. The first derivative is 1 minus x over 2, and so that's what I'm squaring, adding 1 to that, raising to the 3 halves power. So that's what my curvature is at any point x. And so in particular, if I want to know what's happening at x equals 2, I just plug 2 into this formula, and it's looking like I'm getting kappa equals 1/2. And so this means, of course, that the radius of my circle at that point is the reciprocal of that. It is 2, which is kind of exciting. Okay, so it turns out there's a very intimate relationship between this arc length that we just talked about in the last video, curvature that we're talking about now, and what we talked about last week with tangential and normal components of acceleration. They're all very closely related, and here's how. First of all, the tangential component of acceleration, you remember the notation for that is a sub t. T is the unit tangent vector. The tangential component is the rate of change of speed, which is also the rate of change of arc length. The speed is the rate of change of the arc length. So you think of this as kind of like the second derivative, right, of arc length in particular. So you'll also notice that a sub t is negative when an object is slowing down, when a moving object is slowing down. And it is positive as the object is speeding up, and it is only a function of the arc length because it's the second derivative of the arc length. And again, since arc length is some measure of distance, then it makes sense that if we take 2 derivatives of that, we would get some kind of a notion of acceleration. A sub n, the normal component of acceleration, also known as the centripetal component of acceleration. This is a function of both arc length and curvature. It's slightly more complicated, unfortunately. And this is yet another way of thinking about how these things are all kind of interrelated. So you'll notice here, so ds dt is the rate of change of the arc length with respect to time, which is the speed. And so if we square the speed and multiply it by the curvature, that's going to give us um, our normal component of acceleration. And if we just take the second derivative of our arc length with respect to time, or whatever t our parameter is, that's going to give us our tangential component of acceleration. Ooh, a lot of things to remember here. So who cares? Why do we care about all this? One very important thing here is when you're talking about curvature and acceleration is when people are designing roads, or as I've drawn, or not drawn here, I wish that I drew this, or as I've printed here, bobsledding. So you've got these banked curves in a bobsledding track, and if those banks aren't at the right angle, if you're not, you don't have the right curvature to compensate for the acceleration of your bobsled going down the track, you will go flying off the track. And I'm sure you all have seen some videos of this before, where bobsleds back when they were actually built just like going down a hill out on these these tracks that we have today, but just going down a hill, if the bank was either too steep or too low, the bobsled could just go flying off the track, which can be pretty scary for bobsledders. But this also happens, I mean, on highways where if you've got a bend in the highway, you'll notice that the road kind of raises up on the outside of it just ever so much, so that the cars kind of get this extra little push around the bend, and they don't have to, you know, get ruined in any way, I guess. Anyways, this is one reason why one might care about curvature if you're going to be designing roads or very difficult bobsledding tracks or sweet roller coasters one day. Okay, great. So good luck with all this. There's a whole bunch of formulas for how to find the curvature. I put it up on online under files. So just check under the week 8 tab, and you should see all these formulas in one place. And good luck. Have fun. See you soon.